Okay, so here we are with lesson number 6. This is resonance and specifically music on strings. So we learned in the last lesson that only under right conditions can we create standing waves. But of course now we want to know what are those right conditions. And so today we're going to look at strings. Okay? If we want standing waves to be created, there's only certain specific frequencies with which we can vibrate this string to give us these beautiful patterns. And that's the trick with kind of generating these standing waves. So the lowest frequency of a string is called the fundamental frequency. We also call it the first harmonic. And then higher frequencies are simply integer multiples of these of the fundamental frequency. And so those are the second, third, and fourth harmonic, and so on and so forth. There are very specific frequencies that create these standing waves, so i.e. we can only vibrate the string at these specific frequencies so that we create these standing waves. And this is the very premise of resonance, is that, you know, we can't get standing waves just from any frequency. It has to be the resonant frequencies of the string. We're going to find out what determines those frequencies, but let's take a look at what standing waves look like. So this is standing waves between two fixed ends, which is what a string is. String is going to be two fixed ends. The first that we see is our symbol F0. This is our first harmonic. Okay, so N would be equal to 1, and the fundamental overtone, the fundamental frequency. So here is what the wave pattern looks like. There are no nodes between the ends of these strings. Okay, so this is the fundamental frequency in a string. Then if we go to F1, this is of course the second harmonic and the first overtone, and we notice that there in this case is one node, and it's right in the middle, one node between the two fixed ends. Next we have what we'd call the third harmonic. So this is yet the third frequency and the second overtone. For this one we have two nodes in between the ends, and of course you can see them here and here. Last on our list, but of course certainly not last on the overall list, we have 3 nodes between the ends, 1, 2, 3, and we follow the pattern. This is the fourth harmonic and the third overtone. So you'll notice that the fourth harmonic, this of course right here is n equals to 4. Okay, so this is the n number, so this is n equals 1, n equals 2, n equals 3, n equals 4, and the fourth harmonic has 3 nodes, so it always has one less node. What we like to do is be able to relate this diagram and say the length of this string to its frequency or its wavelength. And that is exactly what we have. This is a formula that we're going to see over and over, is that the length of the string, the resonant length of the string, is equal to n times lambda divided by 2. Okay? N can be 1, 2, 3, so on and so forth. So if we have the fourth harmonic of the string, we're going to put n equals to 4. If it's the 8th harmonic of the string, then n is going to be equal to 8, and so on and so forth. Lambda is defined as the wavelength, and of course Ln is the resonant length. So this is our resonance formula for string. Let's see how we're going to work it in a problem. A violin string is 54 centimeters long. The speed of sound in the string is 1,440 meters per second. Draw the string vibrating in its first and third harmonics, and then find those frequencies that are at those harmonics. Alright, so the first thing, this is what we have. So L is equal to 0.54 meters, and that is the length of the string. And then the speed of sound in the string is 1440. We've been asked to draw the first harmonic and the third harmonic. So this corresponds to n equals 1, and this corresponds to n equals 3. So now, I could go and peek at the chart above. Eventually we won't have that chart, so we have to find a way of memorizing these harmonics and what they look like. So the first harmonic has no nodes in between its two fixed ends. So this is what it would look like. The third harmonic has two nodes in between its two fixed ends. So this would be this diagram right here. Let's deal with the first harmonic first. We know that Ln, L1 in this case, is equal to n lambda over 2, and n is of course 1. So we've got L1 equals lambda over 2. We know the length of the string, 0.54. We've put lambda in there, and we can solve for the wavelength. Now, this is useful because we've been asked to find the frequency. We know that always v equals f lambda. We were given the speed of sound, 1440, and that's equal to f times 1.08. A quick division, and we find that the frequency is 1.3 times 10 to the 3 hertz, 1333 hertz to be exact. And now we can repeat the process with the third harmonic. In this case, the third resonant length is equal to 3 lambda over 2, right? Because n is equal to 3 in this case. So we can do something similar. 0.54, which is the length of the string, is equal to 3 lambda by 2. And if we solve for lambda, we get 0.36. Sub that into v equals f lambda, and we find that the new frequency at the third harmonic is 4,000 hertz, 4.0 times 10 to the 3. This is a very typical question for how we deal with resonant lengths on strings. Now, factors that affect resonant lengths, you know, we've kind of seen what those frequencies are. We've seen, you know, standing waves and what they look like. Now what we would like to do, though, is we'd like to look at the factors specifically that affect the frequencies on strings. The first is length, okay? And if you're a guitar player, you know that when you press down on a fret, really, you change the frequency of the string or you change the note, but you're also effectively changing the length of the string in that case. So here, we know that frequency is proportional to 1 over the length. It's inversely proportional. If you shorten the length of the string, you increase the frequency. Here's a little relationship that will help us in solving problems. F1 over F2 is equal to L2 over L1. Again, another factor is the tension in the string. If you play a string instrument, you know that you can crank up or crank down the tension. Tension is proportional to frequency, not inversely proportional, but it's proportional as the square root of tension. Okay, tension is a force that pulls something less or more. And third on our list is the diameter of the string. You know that guitar strings all have different thicknesses, and of course they all have different frequencies. It's of course inversely proportional. The larger the diameter of the string, the lower the frequency, similar to the way that length is inversely proportional. And last but not least is the material or the density of the string. You know that different types of string made of different materials will have different frequencies, and frequency is inversely proportional to the square root of the density. This is the trickiest one of them all. A couple of examples to show you how we deal with this. A guitar string has a length of 0.8 meters and it has a frequency of 375 hertz. When the string is shortened to 0.6 meters, what is its new frequency? Here's what we know. F1 is equal to 375. F2 is our unknown. Here's L1 and L2. So if we use this first relationship, F1 over F2 equals L2 over L1, easiest way once we sub in is that we can cross multiply to get ourselves out of this. 0.6 times F2 is equal to 375 times 0.8. Divide by the 0.6 and we get 500 hertz. Therefore, the new frequency is 5.0 times 10 to the 2 hertz. And really, it's quite as straightforward as that. A piano string has an original tension of 150 newtons. What new tension must be applied to the string to have it vibrate with a frequency exactly twice that of the original? This is a question for you to try, and we'll take it up in class next day.